So let's say for fun over our break, we were reading about an ecological zone in Croatia. Then we took the first paragraph from that Wikipedia article, not the very first sentence like that, like outline sentence, kind of like a thesis statement, but instead like the first kind of body paragraph, maybe we'd say, oh, it's still. Let's say we took that first paragraph there, and we took all the words and we went ahead and well, went ahead and alphabetized them. So you're really good. Let's just say we're really good with Microsoft Word. So we alphabetized them. So we have all of our words right here. All right. So let's talk about why we might do that. So let's say we have to. So we have a good amount of data here, and what I want you to do is, as we're going through this, pretend we have even more data than this. Pretend that it's not just the first paragraph, but it's 200,000 articles, all alphabetized. And let's go and talk about why we might have actually done the alphabetical. So when I alphabetized this, it was actually a little bit of work. I had to put it into Microsoft Word, that convert to text to table, then I converted back to table to text, then I sorted it, then I counted it up, so that way I know there's 51 elements here. Then I turn it back into a table, but in columns only, and then I turn it back into text with these tabs in between. So it was a fair amount of work, and that's something to say. That's a point I do want to make sure that you'll have for later, which is sorting is expensive. We're gonna leave that as kind of like a good general idea. Just put it right up over there. All right, so sorting is actually very expensive. So the question comes up of why sort? Well, the benefit of it is actually to do this thing that we call a binary search. So we have two things that well, we have at least one that we've done so far. This is the second one. And I just want to make sure you can have the difference between binary search and sequential search. Now, sequential search might also be called a linear search. Both names are totally fine. Kind of like our other little maximum. I'm going to put that up here. So let's talk about what this binary search thing is. A binary search, as you might expect from the name, has something to do with twos. And what happens is, let's say we have a list of elements. What it does is it takes the list and it looks at the very most center element. And then it looks at whatever it's looking for. Let's say in our example, we're going to be searching for the word October. So we're going to be searching for the word October in our list of words here. Now, oftentimes we'd be doing this with numbers, so we've been looking for a number in a list of numbers, but we're going to go with words for now, because words are fun. So the first thing it's going to do is compare our query over here. This is our query, the thing that we're looking for. It's going to compare our query with whatever our middle element is. Yeah, there we go. Okay, so we're going to go and keep that up there, just so we have, evidence for where we are, and for the claims I am making. So the claim I'm going to make here is this. We have 51 elements, right? Hopefully you said right. So there's 51 elements. That means the middle element should be element, we're going to call it element 56. Wow. We're going to call it element 26. 26 would be basically halfway between both the 0 and element 51. So we're going to say it's element 26. So this is going to be index 26 right there. And index 26 is the word Ivica, or Ivica. I'm really not good with Croatian. At least I don't know Croatian at all, Nothing against Croatia. Anyway, so we have the word Ivica here. That's our middle element. Now I'm going to ask you a pretty easy question. Is October Ivica? No, it's not. Those are very different, clearly different words. I mean, we can tell because if we compare it letter by letter, okay, that's not really visible. There we go. That's much better. All right, so if we're going to compare we're going to compare it letter by letter, we can see clearly O and I are different because O is way later in the alphabet. I is way earlier. That's what I meant to say. Yeah, so O is way later in the alphabet. So let's go ahead and use that fact to our advantage. I told you this is a sorted list, right? These words are sorted into alphabetical order. So if I'm in the Ivica section, I'm in the I section, well, I'm pretty much guaranteed that if October is actually in here, because that's kind of the point of binary search, not only to find it, but to make sure that it actually is in there, I know it's going to be somewhere to the right of where I am. I know it's going to be somewhere in the index between 26 and 51. I know that 0 through 25, or actually that 0 through 26, have no purpose to me, because this is a sorted list. And because of that, watch this, and remember, pretend that this is a gigantic list, not just the one. Because of that, I can basically just ignore all these. So you know what happens? Is now I have to find the middle element between 26 and 51. So now, let's try this. I'm going to go and find the middle element somewhere right in here. Let's see, the middle element between 26 and 51. Well, let's see, how do I do that? Well, I know I'm going to do 51 minus 26, right? Because I want to see what's midway between there. It's going to be 25. But element 25 isn't my answer. So let me go and divide it by 2. And there I should get 12.5, but we're going to round that down to 12. So let's round that down to 12. Alright, but that's still not my answer, because that's before the i's as well. So let me go ahead and add that to 26, and now we get 38, and 38 is midway between 26 and 51. So in case you missed it, some tough math going on. What I did was, I got the difference between the lower and the higher number, divided it by 2, and then added it to the lower number. By doing that, I got the middle element in between these two indexes. Because remember, I haven't checked any of these indexes to the left of Ivica, but I also don't have to. They are completely useless to me. At least as long as I'm trying to find October. So now that I'm ignoring it, and we can go ahead and check out what's at element 38. Element 38 is the word proposed, right? There we go. Proposed, which is in our list right here. So yeah, proposed. Now here's the thing. You might get a little worried because, oh no, we've shot past it. Because comparing them letter by letter, versus proposed, comparing them, the query and the middle element, because that's what I'm doing each time, I'm comparing query with the middle element. I noticed that that P, is later in the alphabet than October is, the O of October. So that means that it's October, if it's somewhere, is in this space that I'm coloring in. So you know what I do? Well, I cross out the stuff to the right, because I know it sure ain't to the right of proposed. Let me go and get the middle element now. Go and clear some of this out. I'm going to go and do that math equation again, because now I want to find the new middle element. Actually, let me go and draw that. So it's somewhere right in there. That's going to be the next spot I search. So let's see, that spot is 38 minus 26. That's going to be 12 divided by 2, which is going to make 6. Well, in that case, I can just say equals 6 because there's no rounding I have to do. And then I'll add it to the lower bound, which is 26, because that's my new boundary. And that's going to be 32. So at element 32, one of our ofs, I'm going to put that there, of. And well, let's compare those things. I'm gonna actually do something a little different, a little crazy. I'm gonna expand my drawing space here because I have room. I'm gonna compare October, because now we're getting serious, right? We have a lot of letters in common. We're gonna have to really compare things. All right, I'm gonna compare October and of. Well, the O's are the same, so if I'm a computer just going through the step by step, these might actually be the same word. Until I get to the C and the F. The F is very obviously after the C, right? These arrows I'm drawing is having C to the left because I know C means that it's going to be somewhere to the left of these ofs. Alright, we'll go ahead and clear that out. So I know I have to look somewhere to the left again. Just like I just did, where I got to element 32. Now I have to go ahead and get in between element 32 and element 26. Here's where lack of planning doesn't help. And I don't have a lot of space here. But that's okay. We'll make it happen. Alright, so next up we have to get in between elements 26 and 32. And I think you got the idea by this point. You can tell that we're going to get to element 29. So I want this little space right here. It's going to be element 29, and I know it's getting a little hard to read now, but bear with me, please. I'll draw a little circle around it. So this right here is element 29. So element 29 is right here, and element 29 is so right there at element 29, as you saw, and are probably giddy with excitement about, is the word October. Yeah, we found it. So when the computer looks at element 29 and sees the word October, and I'll change it to red so it matches all this stuff, because we've been hunting for this red October for a little while. And so we found it finally, right? So we check our letters of both words, both of the query, which I'm writing here, and of the element that we found, that we finally landed on. And it sees that they're exactly the same. So that means it's done jumping around. Let's go ahead and wrap this up as a conclusion. What was so good about sorting? Again, I went through a lot of work there sorting each of those elements out. I mean, okay, not like a lot, but enough, like that I spent time with that. So you might be wondering, well then what was the benefit of binary search versus sequential search? Binary search has this advantage, that as long as you're dealing with a sorted list, the number of times that you check elements is far, far less. Let's go ahead and count up how many elements we actually compared. And remember, for each of those comparisons, we have to check each letter. Or if it's number, check the whole number. Let's go ahead and check our how many comparisons we had. Remember how I marked each of the indexes that we checked? We didn't check 0, and we didn't check 51. We just started with the very middle index of 26. So that was one time. And actually, I'm going to draw this in a nice blue color right there. So this is the number of times this blue line here. These blue tally marks will represent the number of times we checked elements. So we started at 26, and we got in between 26 and 51 for 38. So that was another one. Then we got in between 26 and 38 for 32. So that was another time. And lastly, we checked element 29. That was a total of 4 times on a list of 51 elements. So for a list of 51 elements, we only had to make 4 comparisons to find our term October. This is kind of why we sorted it. Because remember, sorting, it's more expensive. It's an expensive operation. It takes a little while. It takes time. It takes resources to sort. But there's a benefit to it. Again, imagine this being a list of 100,000 elements. No, 200,000 elements. So let's say that we get to this middle element here at, right here, at about 100,000, right? Because that would be in between 0 and 200,000. So once we found that this middle element wasn't the thing that we were searching for, you know, the word October, we would ignore everything to the left of it and itself. That would mean that we just decided to not make a comparison for 100,000 elements because we don't need to compare them. We would go on to the next part, finding somewhere between element 100,000, between element 100,000 and element 200,000, which would knock out elements 150,000 through 200,000. And I should really say 150,000 through 199,999. But hopefully you know what I mean. So we would just ignore another half of those. So in the first round, we knocked out 100,000 elements. And then the next comparison, we knocked out 50,000 more. And then we get to this middle element here, and we would find that we can remove another 25,000. Because remember, there's 50,000 there in total, and we just ignored half of them. And then we jump into the middle of them. So even if we didn't find October at all, already we've knocked it down to just 25,000 elements that could be possible. Which, when the original list was 200,000, yeah, that makes a big difference. So this binary search is really useful because what it does is, like its name might make you think, you know, bin, binary meaning 2. It splits the list into halves each time, allowing to have what we call logarithmic efficiency, meaning that the very highest number of times that we would ever perform a comparison in any list with binary search is going to be equal to the log base 2 of the number of elements in that list. Now, some of you may not have gone through upper level algebra. Talk to me about it if you need some help understanding that concept. But yeah, so the most number of comparisons that would have to be performed are log base 2 of n, where n equals number of elements. In this case, it was the very highest number of comparisons we'd have to perform is a log base 2 of 51, which yeah, is pretty good, you know, considering it could have been 51. And then considering our case where it was 200,000 elements, again, that's really good. So sorting, though it is expensive, is a worthwhile investment if you're going to be making a search through it. Binary search allows you to cut down the amount of time drastically. All right, well, that's about that. Let's go ahead and talk about it in code next. Moving into coding, let's see just one more example of the background, the theoretical of how this would go. So let's say we have this array of 13 numbers, 0 through 12. Our query is the number 4, so let's go ahead and search for it. So what happens is we start off by looking at that middle element, the 6, right there. Then, noticing that 6 is bigger than our query, which is 4, we go ahead and check the number in between 0 and 6, effectively ignoring the whole right side of the array, including the 6, because we're done with that now. And what I mean by ignoring it is just that when we make our new middle, we're going to do the middle in between 0 and 6, not 0 and 12. So in between 0 and 6 is 3. So let's take a look at 3. Well, 3 is smaller than our query, which is 4. So we ignore that part now. And we ignore it by making the new lower bound 3, keeping the higher bound as 6, and again the middle number in between those. Now the middle number in this case, just using our equation of 6 minus 3 divided by 2 plus 3, which, you know, just because that's high minus low divided by 2 plus low, well, that would get us down to a nice and even 4.5, which then rounds down to just 4. We look at index 4. Hey, look, we found our query. Now, this can also be represented by this kind of this code sketch, we might call it. This code sketch shows how we start off and then just how we go around through it. Maybe this would be kind of helpful for you. Not only am I going to include this as a file for you to download, but we're also going to see it every now and then as we go along coding. So, buckle up and let's get started. So we're going to start off with looking for a string and an array of strings, like how we did in the theoretical part. And I'm just going to get a bunch of random words: aardvark, ant, apple, biscuit, cabin, crutches, dog, dragon, elephant, and mouse. And we're just going to put all those in. It's one nice little array. It works. It's all nice. We're all happy. Okay. So to start off, to get ready to do our search, first thing is I'm going to want to figure out how long this list actually is, which is using words.length, because words is the array's name. I can say that into a variable, as I have done here. You don't have to, but I like doing it. All right, so we'll start the actual binary search in just a moment. But first, let's also define our query. Our query, we're going to look for the word cartoon. Cartoon because it's not present in our words array. And I want to start off with kind of a tough case to see if our algorithm will work. So start off by getting the lowest index. This would be index 0, the A index. You know, in the list of A through Z, A can be considered to be the lowest. Then we have high is going to be equal to the length minus 1. It's the very last index. And then middle or medium is going to be the in-between element of the two, and it's with a hyphen there. Now let's go and get our overarching while loop. The while loop is while low is less than or equal to high, because we're going to keep going until that's no longer true, or until we break out. So the first thing we do in this loop is we reset the middle element, or the medium element, by using the middle formula that we know. Now I'm going to put it in 2 lines. So we start out with medium equals high minus low divided by 2. And semicolon there. And then I'm going to say medium equals medium plus low. So that's me separating out the formula that we saw earlier. You know, instead of being high minus low divided by 2 plus low, it's going to be this than that. Now, compile it, it's all good. Let's do our next part where we have to check if it's actually equal. Remember, that's the very next thing we have to do. Is it actually equal? So if query.equals word at, yes, it's called words. Okay, words at that middle index. If they're equal, then we know we're done. Let's go ahead and break out. Break is where we exit that while loop. All right, otherwise, if let's see, we're going to do if query is actually later in the alphabet. So that means if it is, then then the query is most certainly not in the earlier part. We can tell this because query.compareTo will return a positive number, because if query.compareTo is positive, then we know that that query itself should be later in the alphabet. So with that, we're going to move low all the way up to medium, because low itself is no longer calculated as the first index in the array, or rather where medium is now, because it's guaranteed that none of the elements that came before are our element. Lastly, if query is earlier in the alphabet, meaning that the compare_to method would return a negative number, we won't have to calculate that. We'll move high down, because if query is earlier in the alphabet than the current middle element, there's no reason to check any of the later ones. And that's that nice thing about binary search, is that we get to ignore half of the remaining elements every single time, and then reset the middle element at the beginning of the while loop each time. So after we've ended this, either that word is actually equal to our query, in which case I'm going to go and say, hey, look, next line, query, and then I'll let them know what query we were using, was present, space, let me get some quotes there, there you go. All right, was present in the words array. Okay, there we go. Now, if instead we exited because we didn't find it, then we'll say it was not present. And if you get an error like that, like medium's not been declared, go ahead and start medium off as something. Just anything, doesn't matter. You probably will get that error, you might not. I don't know. So to this case, query was not present in there, right? Because cartoon was not present in that words array. You know, we take a look at that array and we don't see cartoon in there. You'll notice it's conspicuously absent. So I'm going to change it. I'm going to grab cabin, a word that actually is in that array. And look, it finds it. Pretty cool, right? All right, let's go and try another one. I'm going to try, let's try safe, a word that's not in there and is at the very end of the alphabet. Okay, not there. That's good. Let's try mouse, last element in the array. Does it find it? Yes, it does. Let's try the let's try another middle element that isn't in there. Try house. Try that. It is not present in the array. Let me go and add it now in the right place, and at this point now it can find it and says that it is present in the words array. Try aardvark, the very first element in the array, and there you go. Aardvark is present in the words array. All right. So binary search can also be done on groups of integers. In fact, usually we see it done on groups of integers. I just wanted to start off in kind of an unusual way. So we're going to get a list of numbers. We're going to use a list instead of an array this time, just because I think it'll be good to see that as well. Let's just get this filled up with a bunch of numbers, and I'm actually skip an 8 there, so 7, 9, 10. That's not just me being weird. What we're going to do is we're going to try and search for 8, but we won't find it. And that's just going to, be one of our test cases. We're looking at good test cases here, right? We'll see that a little later. Now remember our structure. Let's go and get that structure back here on the screen. All right, there we go. So remember in our structure, we start off by just putting in all those, the low, the middle, and the high. Then we go ahead and go right into that while loop, and then we end off checking to see if we found it or not. In this case, however, we do have all our integers already declared. So now we're just going to reassign those values. We wouldn't say initializing, since initialize really is just for the first time we give it a value. Low is still at 0. Don't set middle at all, since we've already... No, wait, not middle. Medium. Medium. We called it medium in this file, which was silly, but whatever. And then high will be equal to the last index. Remember, that's size minus 1 for an array list. For an array list, it's going to be size minus 1. Moving on from there, let's go and get a query. It'll have to be query 2, since we already have a variable called query. Anyway, so query 2, we're going to look for the number 6. Our while loop, as long as low is less than or equal to high. And then inside the while loop, first you have to have the middle equation, which is just simply high minus low divided by 2, and then add on low, so that way you keep it between the low and high. Earlier, I did it in 2 lines, where I divided by 2 and then added low onto it. So it's 2 lines down here, doing the same thing, but it's just in 1 line. Sure that is pretty clear to you. All right. So first things first, if numbers.get at medium is equal to the query. See, it's a little easier than strings. We don't have to use dot equals. Then we go ahead and handle. For this one, we handle if the number at the middle is bigger than the query. If the number in between the bounds of our search is bigger, then ignore the right half. Also ignore that I used the wrong then there. High equals medium minus 1, so that way it moves high all the way back to where medium is. And of course, if nothing else, move low up to just beyond it. We're going to compile that, sees that it compiles just fine, so no real problems there. Lastly, let's go ahead and do that equality check, where at the end of it all, medium is somewhere, and it's either on the it's on the last index, whatever the case. And either it is query, and we have found the number we are looking for, which I'm gonna show to the user, so that way it's a very nice, user-friendly program. But either we found it, or we did not find the number. We're going to compile that, then we'll run it, and let's see what we got here. So as you can see, 6 is present, and we did find 6. So, that's pretty good. Let's change it over to 7, see if we can find 7. And we do. Pretty cool. Let's go and try 1. Let's test the boundaries. We're going to use something right on the edge. Oh, good. It works. Let's try 12, the opposite end, because, again, good test cases. We're checking all of our numbers. 13, so we're just beyond the upper boundary. Did not find 13. Perfect. 0, just below the bottom boundary. Let's go and try it. All right, 0, did not find it. Very good. Let's throw in a -1 just for fun. And as you can see, no problem with the negative. Has no problem finding it. So let's go and try 8 now. Remember, that was the thing that was missing. And boom, still no problem at all. So, in short, good test cases, they check for both numbers that would be there and numbers that wouldn't be there. Just a good way to test your work when you get to the end of this unit's lab. Now, there is another thing we can go ahead and throw in here. It's going to be a steps count, where we just basically count out how efficient the algorithm is, see how many times it has to check. And we'll actually leave that as something for you to go ahead and complete on your own. Yeah, I think that'd be for the best. Go ahead and try experimenting with that. Be a lot of fun. See ya. So to wrap up, the efficiency in terms of max comparisons, basically, that we should see with binary search is shown below. So remember, it is in terms of log n, meaning the log base 2 of the number of elements is the maximum number of comparisons we have to have. Now do take these numbers with somewhat of a grain of salt and add one more comparison to each of them, because you do have that final check to make before finally having low surpass high. So for instance, when there's only one element, you still do have to make a comparison with that one element. So again, just add one of these. But otherwise, you'll notice in each of them, it's just simply showing what power of 2 it is. For instance, 32 is 2 to the power of 5. So we see there are 5 comparisons maximum before it finds or does not find the value it is looking for. 64 is 2 to the 6th, and 2,097,152 is 2 to the 21st power. Again, only 21 checks, which is, of course, monumentally better than sequential search. Remember that sequential search is in terms of n, meaning if we have 64 elements, it'll take 64 comparisons. If we have 1,048,576 elements, it'll take the same number of comparisons, that many, 1 over a million. So once we start dealing with really truly large values, it becomes very important to do things like binary search. All right, well that wraps all this up. Please let me know if you have any questions.